So in this video, I will talk about Restricted Boltzmann Machine. The Restricted Boltzmann Machine, or RBM, is very different from other machine learning models, and it took me a long time to figure this out. I don't find that there are very good tutorials on the internet where they give you a very intuitive explanation, and most of them will just dump you a lot of mathematical equations. So in this video, I will try to explain this concept in a very intuitive way using the D3.js JavaScript library. It provides some animations. I think these are the questions that have been difficult to me while I have been learning the RBM. So I will try to address each of these questions in the video. So on this web page, you can find two stochastic units, two neurons. Here, they are not stochastic yet. The white represents the neuron B off and has a value of 0, and the black represents its on and has a value of 1. When I click start, they began to randomly switch between on and off. In my code, I engineered them in such that their chance to be on and off in any given time will be 50%. These two neurons make up a very simple Boltzmann machine that has no edges between them. They are just independent stochastic neurons with equal chance to be on and off. So for this simple system, we will have 4 different configurations, whether the two neurons be both on, both off, one's on and one's off. And since these two neurons are independent to each other and has been engineered to be on and off by 50%, the probability of each of these 4 different configurations should be the same as 25%. What I mean by this, if you do some sampling, you just at some random time point, you just took a snapshot of the current states of the two neurons or the configuration of the system. You should observe, and if you sample a lot of them and you count occurrence of each of these 4 configurations, they should be roughly the same. But in the previous web page, the way I defined the probability of the two neurons to be on or off are arbitrary. I just wrote in my code and let them to be 50% of chance to be on and off. To be more scientific, or to be more like the nature of thing, we use a bias neuron to control the probability of the stochastic neurons. So here we have a bias neuron attached to each of the stochastic unit and has an edge drawn between them. A bias neuron is always on and has a value of 1, and they could be grouped together as just one bias unit, but for illustration purposes, I attach a bias neuron to each of the stochastic unit. They could be the same, just be one bias unit. What really controls the probability of the stochastic unit is the weight of the edges between the bias neurons and the stochastic neurons. So to understand how the weight could control the probability, we need first to define an energy function for this system. So the energy function of this simple system will be the minus the weight of the bias neuron of the first stochastic unit multiplied by the value of the first neuron, and minus the weight of the edge between the bias neuron and the second neuron and the value of the second neuron. This is the energy of the state. This is the function how you can calculate the energies of the different configurations of the system. So why do we need to define energy for the system? Because we want to assign qualities to the different configurations of the system. So we define that a system with a lower energy is a better system and our preferred system. In terms of why we define energy this way, is because if you define the energy in this way, the probability is easily calculated for each of the different states of the configuration. In essence, you can basically define the energy in whichever way you like. You can even add some quadratic terms and exponential terms and do all the complex square root things. You can add any mathematical operations into the function, and you can call it an energy function at your will. I think that all qualify energy function for this system. You can basically write any equation for this system to be the energy function. But if you wrote the energy function in other ways, it will be very hard to define the probability of the different configurations of this system. But if you write them in this way, the probability of any given configuration of this system will be proportional to the e raised by the negative of energy function. And specifically, it is calculated by this e term exponential term of the current state divided by all the sum of all the e terms of all the possible configurations in this system. For this system, the denominator will simply be the sum of this exponential terms of these 4 different configurations. So that's the reason why you want to write the energy function in a very specific way, and why you want to define it. But in this example, the energy function is the same for all the 4 different states, because the weight is always 0, so the energy will be 0 for each of the 4 configurations. And you can, according to this formula, you can easily know that each of the e terms will be 1, and the probability of each of the 4 configurations will be 1 divided by 4, which is the sum of the 4 ones of the 4 configurations to be 25%. So this is how the weight control the probability. In this case, it's exactly the same system with the previous example, but with the probability defined by the weight with the bias neuron. And if we assign the weight differently, if we assign 2 to the weight between the bias neuron and the second neuron, and negative 2 between the bias neuron and the first neuron, we would expect that the system will prefer the second neuron to be on and the first neuron to be off, because when the second neuron will be on, this term will be large and the minus of this term will be small, so add the energy will be small. And when the first neuron is on, this term will be negative and small, and the minus them will be large. So we do not want to, the e function will be large. So we want it to be 0. So we would expect to see more like this configuration. If we will start this system, we can see that as the time proceeds, this neuron is mostly on and this neuron is mostly off. If we do some sampling, and you can say it's not like the system is stochastic, so you can still see all the 4 different configurations, but mostly the second neuron tend to be on and the first neurons tend to be off. So this is how the weight of the bias neuron could control the probability of the stochastic neurons. And by tweak the weight of these weights, you can get the kind of distributions of configurations you want. And in this example, I have set the weight with the bias neurons to be off for both the neurons. So I will not show the bias neuron here. But now I connect the 2 neurons with the weight and set it to be 2. And by the way, and this is not a restricted Boltzmann machine. I want to say is like these 2 neurons are both the visible neurons and in the sense of the restricted Boltzmann machine, because they are used to model the sample distributions. And that's why here I use V to represent the values of these 2 neurons. The restricted Boltzmann machine, it does not have connections between visible neurons. So this is actually, for now, this is a Boltzmann machine, a general Boltzmann machine. So in this case, the weight between the two neurons are set to be positive. In the previous example, we defined the energy function of the system as only the multiplication between the bias neurons and the stochastic neurons. But when there are connections between the stochastic neurons, we need to add a quadratic term, which is the weight multiplied by the first neuron and the second neuron. In this system, the weights with the bias units are set to 0. So we only have this term, which is the value of V1 and the value of the first and the second neuron multiplied by their weight. So what kind of distribution of the configurations are you expecting to see for this system? Based on this function, we can say that the system prefers that the two neurons to be on. When the two neurons to be on, this multiplication will be positive, this multiplication will be large, and minus this multiplication will be small. So the energy of the system will be small. So the distribution should be that this configuration where the two neurons are both on will be the most frequent. We click start, and we can see that the two neurons tend to be on together. And then we just do the same thing as the sampling. And you should see like this occurrence, this configuration occurs more. It may not be exactly so in this small sample. If you sample them enough time, you should mostly see this configuration to be the largest proportion. So this is actually the way that you can use a weight to encode the correlation between the two stochastic neurons. And if we set the weight to be -2, according to this function, the energy will be large only if both neurons are on. And as long as any of them is off, the energy will be 0. So these three different configurations will have the same probability, and these particular configurations will have a lower probability compared to the other three. So if we start the system, we can say like we rarely see the state where both of the neurons to be on. And if we do the sampling, we can see this configuration does not occur as frequently as in the previous example. And you can calculate the exact probability of the occurrence of each of the 4 different configurations using this function. And if you sample enough times, the occurrence of each of the 4 configurations should match your calculation. So then the next question I want to address is why we want hidden units. We want hidden units because, for example, in the previous 2 examples where we can only have connections between 2 visible units, the distribution of the 4 different configurations we can encode is very limited. We can only encode distributions where this on configuration is large, or better, this on configuration is small. But we cannot configure other distributions of the configurations. For example, we want this particular configuration to be large, and we want to encode anti-correlation between the 2 stochastic neurons. With only one edge between the visible neurons, we can never do that, because even if we assign -2 and to the weight between the 2 neurons, they won't be anti-correlative. They will have equal possibility of these 3 configurations. But first, in this example 6, I want to demonstrate that with hidden neurons, you can still encode the distribution of the 4 configurations as you see in previous example, using an edge between the 2 visible units. So here, this neuron is the hidden unit, and we have no connections between the visible units. So this is a restricted Boltzmann machine, and it still can encode the distribution of configurations as you've seen at the previous 2 examples. What we do here is set the weight of the hidden unit with the bias neuron to be very large. So the hidden units despite the fact it is a stochastic unit, it will almost always be 1. And then we set the neurons between the hidden and the visible unit, the hidden units between the hidden unit and the 2 visible units to be both 2, and it should be exactly same. It should encode exactly the same distributions as example 4. And if we set the 2 weights to be negative 2, it will be it should encode exactly the same distribution as example 5. So I won't run this example. It's very simple. Now come to the example 7. Here is the setup of the weights between the hidden and visible units so that the whole system will encode some anti-correlation between these 2 visible neurons. This is a distribution that can never be encoded without the help of hidden units. So from the weights, can you infer what is the preferred configuration of this restricted Boltzmann machine? Yeah, it's a configuration where the hidden unit is on, the second unit is on, while the first unit is off. So let's do some mathematical calculation first. So the first column lists all the possible configurations of the system with the hidden unit. There are 8 different configurations possible for this system. And the second column lists the energy for each of the 8 configurations. We can say this is the preferred configuration of the system. It has an energy of -2. And this configuration is not favored by the system, which has negative or +2. All the other configurations have equal energy of 0. And if we calculate the exponential terms of all these 8 configurations, these are the values and these are the total. So according to the function I listed here, the probability of each of the 8 configurations, including the hidden unit, is basically this value divided by the total. So these are the probability. So we can say that the system prefer this configuration. But a very important idea you should get from the restricted Boltzmann machine is that we don't really care about the state of the hidden unit. What we really want is to use the invisible unit to encode the distribution. So we only care about the configurations of the visible unit. So this is the probability of the 4 different configurations of the visible units. This value is basically calculated as the sum of the 2 global configurations where the visible units have the same states. So when the 2 visible units are on, its probability will be this value. And we can see that the system we have created prefer the state where the first unit is off and the second unit on. It has the largest probability of 6-2. And it does not favor this configuration with the first unit is on and the second unit is off. So in this way, with 1 hidden unit, we can encode the distribution of the configurations of the visible units that is not possible without the hidden unit. So my understanding of the restricted Boltzmann machine is that the hidden unit is just a structural or scaffold like helper unit, which by itself doesn't mean anything. It just has a structural support for the whole system so that the whole system could afford in a more sophisticated way to encode more complex distributions. And one thing I think I'm in different opinion with most popular tutorials is that most people will say that the hidden units actually encode the distribution of the visible units. But in my view, I see the hidden unit as a structural support. What really encodes the distribution of the visible units are the weights between the hidden unit and the visible units. So it's weight that matters. It's the weight that actually encodes the distribution of the visible units. How could you think that a stochastic unit could encode some distributions? If you want to encode some stationary probability distribution, you have to have some fixed parameters. I think it's the weight that are actually fixed in the system, and the hidden unit is, you can just think them of as a structure support, so that you can connect the edges as the way you want. So all the mathematical stuff you learn about learning the restricted Boltzmann machine is to solve the question that, given the distribution of the visible units, how could you find the weights that best encode the given distributions, which is a topic that is not covered in this video. If I have time, I will probably make another video to explain that. But I feel it's not very necessary, because I think most other tutorial focus on explain how you can derive the mathematics to find the weights that encode the visible units, but not many tutorial really tell you the essence of the system. So I think most of you can learn the way to find the weights for the visible unit distributions from other tutorials. So we can still do like a sampling like this. So like just by eye, if you observe long enough, you should see that most of the time the system prefer the configuration where these two units are on, and this is off. If you do some sampling, you should mostly see like this configuration, but it doesn't look like so, because we only have one system, and we probably click them too fast. And another way to think of the distribution is that, imagine you have tens of thousands exactly the same system, and you let them run a few time steps, then you count the occurrence of the configurations of the visible units in all of these identical systems. You should find like roughly the same distribution as here. To really prove that my system actually works as I expected, I have a 8 example where in the 8 example, you won't see anything on the web page, but if you open the console of your web browser, what it does, you will see some prints. So what it does is it construct, I think if I remember correctly, 1,000 identical systems, as you'll see in example 7, and run them 1,000 times, and then count the frequency of the occurrence of each of the 8 configurations. And here shows how many time steps the system has passed. Okay, if you type frequency, it will give you the output. And you can say like, so the false and the true represents the states of the 3 neurons. There's the first visible unit, the second visible unit, and the third hidden unit. And you can say this is actually the favored configuration of the system, and their frequency is roughly the same as I calculated here. So which basically indicates my system works as expected. At last, I want to speak a few words about the concept of thermal equilibrium. I don't expect to say too much that question arise from this very simple system. It should settle into the thermal equilibrium as soon as like only after several time steps. But if you have a very complex restricted Boltzmann machine, the initial states will affect how the system evolves towards the desired distribution. So you need to have some time steps for the system to converge to the ideal configuration. So that's called a thermal equilibrium. It's just a memory of the initial states that are different from the distribution encoded by the system. This is the end of the video. So there are a few take-home messages I want you to take. So The first is that it is the edge weight that really controls the probability of a unit to be on or off. And the hidden unit serves as a helper or scaffold to help encode more complex distributions of the global configurations. And given the RBM structure, it is the edge weights instead of the hidden units that control the distribution of the global configurations after the system reaches the thermal equilibrium. So it's not the hidden units that control the distribution, because hidden units they are stochastic. How could stochastic things encode some stationary distribution? Yeah, I think these are the most difficult concepts one will encounter when learning the restricted Boltzmann machine, and I hope the video to be helpful.